Thank you very much. So let me start by thanking the organizers for constantly inviting me to swim, and hopefully the weather will improve and we will swim well. So, I decided not to repeat. Although we have some progress, what we were doing with Petro, I decided not to repeat. So I decided to go to amplitudes. And so it's very orthogonal topic to this workshop, but I will talk about amplitudes, but then I will switch to Chern-Simons and other theories. So let me tell you something about amplitudes. And again, my discussion will be oversimplified, and I will try to explain you what I'm talking about. So amplitudes in gauge theory, it's a big, complicated subject, and basically people observed, so if you take a generic amplitude in the gauge theory, it more or less looks like follows. So you take your amplitude, which is, some gauge invariant quantity. So you have some momenta. I will write for you example. And it's basically looks as sum of a particular bunch of graphs. So first I will tell you general statement, and then I will give you example, and then I will switch to Chern-Simons. So basically, you will have the following factors. So you will have this factor which is called color factor. Okay. Then you will have some kinematic factor, which is composed from momenta. And then you will have downstairs some basically momenta, which is roughly speaking looks like a scalar propagator. Okay. And now this is very generic. Whatever gauge theory you would take, you always can decompose. So there will be color guys, which I will give you example in a moment. These guys, which can be very complicated, organized. And then this will be this scalar propagators. And basically color kinematics, it's about properties of these guys. So let me try to explain on very simple example what I'm. Yeah, absolutely. So let me try to explain for you a very simple example what I'm talking. It's just a graph. It's a Feynman diagram, and that's all. And it can have loops. It can, of course, if you have matter, your Feynman diagrams can be sort of colored, very complicated, etc. But what's amazing is that, whatever complicated theory you have, you can write always like this. And experimentally, people observed very special properties of these factors, which looks very mysterious. So let me start from very, very simple example. So imagine I have a gauge theory, and I would have just 4 external guys, and I write for you something like this. So I will have this diagram. Let me write A, B, C, D. Then I will have this diagram or this graph, A, B, C, D. And then I will have correspondingly this graph. So this will be A, B, C, D. So this is famous S channel, T channel, U channel. Okay. Then, of course, I can write for your color factors, which is this color factors is the following. And this will be true for any gauge theory with some Lie algebra. L, F, L, C, D. So this is, they're constructed according to this graph. Then these guys, CT will be F of B, D, L, F, L, C, A. And then this will be S, U, F, D, A, L, F, L, C, B. Okay. So then for this graph, my amplitude will look as follows. So it will look as NS, CS, DS plus NU, CU, DU plus SNT, CT over DT. So now what you can see that, of course, if you stare at these things, long enough, then basically some of these four guys, this is just a Jacobi identity. So CS plus CT plus CU is equal to 0, and this is just Jacobi. Okay. So it means that the gauge invariance of these guys is the following, that if I take my Ni and shift my Ni by any function alpha di, then my amplitude will be shifted by the following things. A goes to A plus alpha on C S U T. This is, of course, 0. So this is basically gauge invariance at the level of amplitudes. So these combinations, whatever, so I mean, they can be complicated. I will write you in a moment for Chen Simons to discuss this stuff. But this, of course, for individual graph is not gauge invariant. So you can basically change them like this. The amazing fact, and this is basically about color kinematics, what people observed on many different theories is the following fact, which is experimental fact. So fact. So there exists a choice of these guys. So there is a specific choice when you can basically write the following identity. So basically these kinematic guys start to imitate this, the algebra. So that's why this, again, I'm oversimplifying story. Of course, when I'm going to more complicated diagrams, you have to discuss. There are a lot of issues here. But basically, this is roughly what's going on. So, and that's why people started in the literature to speculate about kinematic algebra. Okay, so there exists a choice. It's experimental fact, has been checked in many theories, at trees, for some theories with loops, etc. And it's not that its fact is proven, but there exists a gauge when basically a kinematic factor satisfies Jacobi-like identities.
Is it understood what is this gauge? Like in special?
No. I mean, moreover, what's important when people do amplitudes, they are not thinking from the action principle point of view, etc. So they write some ansatz, which is Lorentz invariant, etc. And then basically you even don't know if this gauge is local or not. So it's not clear. You do it in theory by theory, and then you just find that these relations hold. It's a
There's no common part in each theory, choice is different.
Yeah. Because also what's important, again, this is feature of any gauge theory. So, but of course, once you change your theory, these factors change drastically. So you have to reprove it again, etc. But it's experimental fact. People see it. And this goes under the name of either color kinematics or BCG relations. There are sort of some subtleties. So there is another fact which is very interesting. I'm not going to talk about it, but let me mention why it's interesting. So why these relations produce so much excitement, because you may not care, but there is a story of double copy. And again, this is actually experimental fact as well. The fact is the following, that if you take this relation and you write now for you another amplitude when you take the same graphs, and now instead of color factor, you will just, so you had Ni and then you have Ci, but then you replace by the same factor. So you just do this replacement. Then this amplitudes always amplitudes from some gravity theory. No, so what you are doing is, you are doing this experimental. So you take a gauge theory, okay, you calculate these factors, and then you find appropriate gravity theory which amplitudes exactly correspond.
How the answer looks like appropriate gravity theory?
It's a supergravity depending. Oh, it's the question is that it's, I mean, this is not understood fundamentally. It's experimental factors observed. It's unclear in which gauge, yeah. But this is why it makes problems so complicated, because it does not look like a well-posed scientific problem. Because as you know, when you choose a gauge, I mean, this is nightmare. I mean, this is not scientific choosing the gauge.
From spin 1 amplitude to make a spin 2.
Exactly, yeah. Yep.
I remember browsing through some papers where people were claiming that via some PV homotoppical approach, they could actually prove this statement. Now you say that everything is experimental, so question is simply.
Okay, I'm a BV person, so I can tell you that all the statements are bullshit. I mean, because these people don't understand how people calculate amplitudes. It's two communities. Amplitude people don't understand what's, homotopy transfer or whatever BV is, and other people don't understand how to calculate amplitude. So that's, it's very, very tricky thing. You should not oversimplify the problem, because if 1,000 people are doing something and then some other guys come and say they claim, I mean, they prove everything and those guys don't understand, then there is something wrong. Yeah. So, I mean, they're oversimplifying. There are a lot of, statements, and people try to write its formula, etc. But it's very, very hard to make a precise. And as Andrei said correctly, because of gauge fixing, it's not a very scientific problem. I mean, it's very hard to pose it correctly.
Yeah, if I remember, we're just saying something like, we know we can simplify things.
No. I think it's overstatement, and I think one has to go slowly. And I'm not going to prove for you these things, but I'm going to hopefully go from a couple of theories and tell you how it roughly works. And it's very intricate property, and it requires much more. But I know these papers, and I think it's oversimplification. I mean, yeah, absolutely, yeah. Any other questions? Okay, so this is the general statements roughly, but let's now go back to Earth and let's start to look at concrete theories and basically try to slowly understand what is going on. And what's the best theory we can do? It's Chern-Simons. Of course, Chern-Simons, it's a bit of cheating, because there are no amplitudes, gauge invariant amplitudes. I cannot look at on-shell amplitudes because it's topological theory. But let's for the moment ignore this fact, and let's do it anyway. So I'm going to do a very weird computation which you're not supposed to do. So I will look at Chern-Simons theory. Chern-Simons theory on R3. And I will look, R3, and I will look at basically calculate amplitudes, but off-shell amplitudes. Again, if I put them on shell, as I'm supposed to do, everything is trivial, but so I have my favorite Chern-Simons action, of course, R3 ADA, so trace plus 2 over 3 A cube. So I will use this normalization. One over 2 for the future 1 plus over 6 A B C F A B C. So for the moment, let me just look at trees only. So I don't want to look at any ghosts, etc. So I will just do trees, and that's all. So what I need to do, I have to take the section, fix the gauge, and then, basically try to calculate the trees in the theory and see what's going on. So let's go to our favorite gauge, which would be a Lorentz gauge. Right. So now what I need to evaluate the section and the Lorentz gauge, and basically try to write for your Feynman rules in momentum representation. So, so remember that Lorentz gauge, just local guys, it will be this. So of course I can solve it in the following way. So I can write this as a d nu some lambda nu mu a, or alternatively, which is in flat space, is the same thing, mu rho d nu psi rho a x. So this is just on flat space solution of this gauge. Now, if I want to write a momentum representation, so let me write some stupid factors, 2 pi 3 over 2, d3p, ixp, epsilon mu nu rho, p nu psi rho ap. So now, also just to avoid additional things, because these guys I can shift by any function multiplied on momentum. So typically you impose this type of conditions to avoid any further things. So my goal is the following, right? So I want to do a Feynman rules for Chern-Simons. So again, it's a very weird calculation because we would think that this is topological theory. But I want to pretend that I don't care that it's topological. I calculate here just 3 amplitudes, so I need to evaluate my action on these guys where I impose the gauge. So let me tell you what's the answer and why it's interesting. So there are two, again, of course, I'm not going to tell you, how to do this calculation. This is straightforward. This is rather trivial, but let me write 2 terms. So what you find surprisingly, at first messy looking result, but it's actually nice. So the kinetic term will look as follows. It will be psi a mu p psi nu b minus p. Then this will be this object which I defined in a moment, p square eta ab. So this object, this will be just a shorthand for minus I epsilon mu nu rho p rho. And then on appropriate space of functions, what I will have, of course, this type of identity. So this p nu sigma p will be equal to p square delta mu. Sorry, mu sigma. So my propagator will look as follows. So if I would have propagator, it looks as so if it's a mu b nu mu nu p square eta ab. Okay. Now I have to evaluate on these guys corresponding to the vertex now. So of course this is a bit more messy, but still straightforward. So I will have d3p1, d3. So what I'm evaluating this term, ABC. Okay, and I will have d3p1, d3p2, d3p3, and then I will have this polarization vectors, a sigma p1, a gamma b p2, a sigma, a c phi p3, and here will be some object which I'm not going to write for you, but let me write in this form. It's a lot of momenta, contractions, etc., but you can write like this: p1, p2 minus p3. So this will be, of course, inside delta function, and then you will write delta rho phi of minus p3. AB. So how this exactly object looks like, it's not important. What's important thing that this guy is actually is antisymmetric in exchange of all these indices, sigma, gamma, phi, together with momentum P1, P2, P3, and of course ABC. So you do this stupid, straightforward calculation, right? So it means that what is going on then, when you would write your Feynman diagram, so you will write a vertex. So what you will have this A mu, P1, B nu, P2, P3, then you will have sigma gamma, and then basically what you will stick, so let me not repeat, but you just stick this object attached to this vertex, and you do the Feynman rules. Now, what's amazing about this object that what you can do, you can derive this f's in totally different way. So I'm doing things slowly, I will explain to you. So I do momentum representations, but then I will switch to the invariant setting without momentum representations and explain what's going on. So these f's, and that's why, I wrote them, you can get in the following way. So let's just for the moment pause and introduce these operators. So let me take L mu, P, and write with this operator. So this is stupid factor I, P, X, epsilon mu, nu, rho, P, nu, dx. So these guys are bases. So this is a basis for divergenceless vector fields, or which is the same for volume preserving vector fields. Vector fields. Right. So I can contract this with any. So it's like, any vector field which would be vector preserving a divergenceless, I can just integrate with P and this will satisfy this property. Yeah.
Very quick question. So you started with a theory that was topological,
Right.
So now you're using P dot X. Are you using the metric?
No, of course I start to use a metric because for the gauge fixing, remember that if you want to do a gauge fixing, even in topological theory, you have to use a metric. There is no way. So I use a metric. So I'm doing something illegal. You typically never calculate the scattering amplitudes in topological theory, but let's do it. Okay. It's.
The question is, does the final answer depend on this metric? There was a long story that people were proving that actually it doesn't depend.
It does not depend. But since in my case, it will depend because I'm doing illegal calculation. Right.
So you're computing not right quantities.
Absolutely. But this is a toy model because eventually I want to basically understand what's going on, right? You first take a toy model, you do illegal things, and then you try to go to physical stuff, etc. But right, exactly. But you see, if I will start, I know a lot of things about Young Mills, but I don't want to even start to talk about 4D Young Mills. It's too complicated. So I'm trying to illustrate with this feature in here. And also important thing that one of the statements I will tell you that any good theory is Chern-Simons in some sense. Anyhow, so let's take this divergenceless vector field and let's calculate their brackets. So again, it's a straightforward thing. You take L mu P1, L nu P2. If you calculate it, you will get this object L mu rho P1, P2, P3, rho P3. Okay, so this object and that object are identical. So actually what you have here, so you have two sets of structure constants. You have a structure constants for Lie algebra. You have a structure constants for volume preserving diffeomorphism there. And then you have some analog of invariant metric, and that's why I mentioned to you the things. However, what's most important thing, so just one statement why this is not a symmetry of this theory. So I erased these things, but what's important thing that when I will write to you these things, so I would have this mu nu p square eta ab. So this is not a symmetry, and this is not a symmetry because this p square screws up everything. Okay. So of course, if I would remove by hand p square, then this would be like sort of copies of two Lie algebras, because if I remove p square, it will be Lie algebra, finite dimensional Lie algebra, and then there will be infinite dimensional Lie algebra, where so this is invariant metric, this is analog of invariant metric, this is structure constant, this is invariant metric, so all indices down, etc. But p square screws up everything. But this is what we have. Okay, so this is very simple fact, and it's very weird calculation, but let's try to unwind. Any questions about this stuff?
So you're saying that this, so if you just go to Lorentz gauge, then you get on the nose these kinematic structure constants, and you figure out these structure constants for some particular vector fields.
Right. Right. So again, this people wouldn't, this is illegal calculations. But still it's good to do illegal calculations. I think it's what Marr and Hendrik in slightly different form realized a few years ago. But again, it's a toy model. Now we need to unwind and ask what is going on, etc. But important thing is that what I'm telling you, very funny fact, which you would not think, but for example, in Lorentz gauge, and this also true for the compact manifolds, etc. You can basically see that there is a pairing between these two types of structure constants. So there are another set of structure constants appear. And again, I'm insisting is that these algebraic structures are not symmetries because this p square screws up everything. Okay, so let's do this sort of more formally and better, and this without momentum representation. So of course, one of the things is to understand what's a property of gauge fixing, which guarantees the things and stuff like this. So let me start some basic stuff about, again, in some communities, this is very well known, but so I have a Lie bracket. So we have a Lie bracket for vector fields. So of course, you know that vector brackets for, so for example, let me see, mu. So it can be written like this, right? D rho V mu minus V W rho, V mu, right? Definition. So let me do the following things. Of course, as you know, I can replace these partial derivatives by covariant derivatives for some metric. Nothing changes. Okay. Then if you can rewrite this stuff in the following way, again, in math community, what I'm telling you is well known. So I can rewrite these things as follows. I can write this stuff as rho, V rho, W mu minus W rho, V mu minus rho, V rho, my plus okay. So this is rewriting. Now what's important thing if you start this relation, so this is a trivial identities. But what you can do now, if you can take these guys and you can send, I'm using metric, so I know that one forms can be mapped to vector fields using the metric. And another thing is that the d dagger acting on V, this is the same as V mu. So now I'm thinking about V as a one form. So it means that I can actually, for you, introduce the following bracket. So if you stare at this guy, and I will write A1, A2, write d dagger of A1, A2, minus d dagger of A1, A2, plus A1 d dagger of A2. So this is a Lie bracket. So this is a Lie bracket on differential forms. So it's known basically for math people, for people who like math. So d dagger is not a derivation on the differential forms, and its failure of being a derivation gives you actually a Lie bracket. Again, calculationally, that's how you can see. So you can map a Lie bracket on vector fields to differential forms. Of course, it's not canonical operation, requires for you the introduction of the metric. But whenever you have a metric, you will have a Lie algebra on differential forms. Now about Lorentz gauge. So when you go to Lorentz gauge, right? So you impose the d dagger of A equal to 0. So A in the image of d dagger. So if your A is in the image of d dagger, then these terms vanish and you get a subalgebra. Yeah, sorry, in the kernel. Right. On a flat space, it's the same thing, right? Yeah. On a compact space, they will differ by harmonic forms. Okay. Yeah, it's in the kernel, and also, so this is will be subalgebra. And moreover, also image of d dagger is subalgebra. By the way, what I'm telling you, it's true for compact, non-compact, for curved manifold, etc. This is not. So in general, for compact guys, so just comment is for compact guy, what will happen that kernel of d dagger is kernel of Laplacian plus image of d dagger. And this will be algebra, this will be algebra. And also what's interesting is that kernel of d dagger, this kernel of d dagger will give me image of d dagger, of course. So this is, because my bracket is always will be written, so this term vanishes and it will be d dagger of something. So this will be in an image. Okay, so there is this bracket on one forms when I put a Lorentz gauge, but of course this is not all. So there is something else you can have to discuss, because as you saw from previous example, I also had some invariant pairing. Right. So imagine I have two forms, A1 and A2. So I will, for the moment, discuss image of d dagger, and the difference between is not that big. It's just kernel of Laplacian, but on flat space, this is two spaces are the same. Okay. So what I can do is the following. I can introduce for you a pairing. So this is a definition of the pairing for any two forms which is on image of d dagger. So if my AI is equal to d dagger of psi I, then I can write this as the integral of A1 which psi 2. So this is a definition. So this is my pairing. Okay, so then you have to argue that this pairing is well defined. And what's important is that it actually does not depend on the choice of this size. Because if I shift psi by d dagger of something, this will vanish because this guy is also in the image of d dagger. And remember, for d dagger, although it's not a derivation, there is the following property for differential forms that d dagger of A wedge B is equal to minus 1 over A d dagger of B. Okay. So this is a pairing. Now what's important about this pairing, that it's actually what you can show, that if you start this formula and that formula, you can show that it's actually invariant pairing algebraically. So let me, so you can prove the following fact, that if you have A, B, A, C, so again, bracket is defined like this. So these terms are gone for me. I'm looking at the image of the dagger. I define for this pairing. Then I will get for you this property minus B, A, C equal to 0. So basically what I'm doing is the following, just to give you an idea. So I have my term A, B, A, C. So I evaluate this, this is by definition is equal, right, A, B, D dagger of psi C, right? Because I evaluate on the image of D dagger. And this, of course, I can write for you as a D dagger of A, B, psi C. And then you can see that this is exactly a bracket, and this with this, it's a pairing. So then I will get as a bracket of A, B is AC. Okay. So what's upshot? You can, any questions?
You're using, of course, the Lorentz gauge.
Yeah.
If you add also ghosts, then does the structure become dependent on the choice of the?
No, it still will depend, but I will get basically, I will tell you in a moment. So I will do this in full superfields, and you know, it will all works here. Now I'm basically outlining for you some algebraic structure which people tend to ignore, but they're there. And of course, they depend on the gauge. I mean, this is what's weird. I mean, typically we will always ignore the gauge, but we shouldn't. Okay, so any other questions? Yeah.
Is this pairing kind of dual to the number?
Yeah. So for people who basically know other stuff, it's familiar pairing. But what I'm basically stressing is that this pairing behaves very nicely with respect to this bracket. So now what's important, so if you put everything this together, right? So what's upshot? The upshot is the following. So we have our Chern-Simons section, which was written as A, D, A, B, eta AB 1 over 2 plus 1 over 6 A, B, C, F, A, B, C. Then we evaluate the section on the image of D dagger. And this section now can be written as follows. So this section of Chern-Simons can be written as following. Is 1 over 2, this pairing of A, Laplace B, eta AB plus 1 over 6 A, B, A, C of A, B, C. So instead of, so basically now, what I'm repeating for you, again, it's very straightforward exercise. So this is Laplace operator. So what I'm telling you now, it's independent of momentum representation. This can be done on curved, non-curved manifold, etc. But in Lorentz gauge, if you evaluate this guy, then you can basically write like this, and there are structure constants which are appearing, here. So this is again invariant pairing. This is a bracket, again invariant pairing, and again these structures will be a symmetry if not this Laplacian, but because of this Laplacian, this is not a symmetry. Okay? So now let me answer Julia's question. Of course, having any ghosts, etc., everything works perfectly here as well. So let me tell you. So you can look in different ways, but sort of either you do this Fadeev-Popov thing here, and as people realize that you can use superfields in gauge fixing, or in principle there is this more advanced technology which is BV machinery, which basically saying is the following, that if you take your manifold, if you don't know these notations, it's okay. So basically what you can look now, you can write your superfields as a function of x and theta, and you have basically theta 1, theta 2, theta 3. So there is this basically BV extension of Chern-Simons, which can be written as follows: A, D, A, B, eta A, B plus f of A, B, C, A, C, A, B, C. So D, this is just basically the Ram differential, but in superfields it's just this operation. So if you take this section and just restrict to one forms, and in this story, this is what's called physical field, this is exactly goes here. Okay. But typically what you need to do, there is a standard story in BV, you have to choose a Lagrangian, etc. So now what you are doing is you basically have to require that your fields A now, so it's differential forms, now fields A are in the image of the dagger. So there is again mathematical fact. Mathematical fact is that if you have now all differential forms, D dagger generates a bracket. So of course, what's important about this bracket, that if you start to look at this bracket, for example, in different degrees, you have to study. So for example, in degree 0, the bracket is 0. In degree 1, here it will be this volume preserving diffeomorphisms. And for example, they will act on this space, etc. So you have to study all these guys. And now you can actually repeat everything what I told you. So if your superfield in the image of the dagger, you can still introduce this pairing as before. Now the only thing, the difference is that you do this in these superfields and you keep all degrees of forms. And then of course, whenever degrees do not match to 3, this pairing will be 0. And then of course you will have a bracket on your superfields. Okay. So let me write the dagger here. Okay. And then basically what I'm telling you, that you can rewrite everything now with superfields. It will, so basically the theory will work. You will have color kinematics. So you always will construct the structure constant. The only thing that these structure constants will have a different meaning depending on degree, etc. So there are a lot of relations. Okay. So this is toy example, but what's the moral? What is going on here? Any questions? So what we like it in this story, that we started from Chern-Simons, right? So we have Chern-Simons theory here, which we generally like. And then we went to gauge fixing. And for gauge fixing, I like this D-dagger operator. But let me just stress which property of this D-Dagger operator I like. So basically, I wanted to have some D-Dagger operator generalized. Well, this story of degree -1. And then I basically, if you will go through all these manipulations which I did to writing things like this, because I like this form, what I need is the following things. So there are 3 properties I need. And so I need that D-Dagger squares to 0. Then I need that D with D-Dagger. So D, it's this operator, but in principle it can be more general. I will tell you in a moment another example. It's a Laplace operator. And then also I need this integration by parts. Okay. And another mathematical fact is that actually the fact is that this operator generates you a bracket. This is a D-Dagger. It's called is a second order operator. So I don't know if you know, so the order of operators can be defined algebraically. You just take a nested commutator, and depending, if you have to take 2 nested commutators and things are vanished, it means it's a second order. If you take 3 nested commutators, etc., so you can define the order of operators algebraically. So this is basically, these properties are important for me to do these manipulations like this. So again, think what I have. I have abstractly some theory which is written as a formal Chern-Simons. And I would like to basically pick up some gauge fixing in such a way that this will be, have this form and this will be a bracket. So formally I need to find for you D-Dagger operator of degree -1 squared to 0 gives me Laplacian. It satisfies Stokes theorem. And if it's a second order operator, then this will give you at least this off-shell color kinematics. So in a moment I have like maybe 10 minutes. I will give you example, first non-trivial example of 2D Young-Mills, but let me tell you that of course 4D Young-Mills, the physical one, can be written like this. So whoever read the book by Castello should know that there is this form exists. The only problem is that these superfields are not freely generated. So it corresponds to differential gradient algebra, but they're not freely generated. But you can write like this. And you can actually construct this operator. The only problem is a high order. It's, but again, it's high order, but it still have a bunch of nice properties. But I will not talk about 4D Young-Mills. This is maybe we will leave for next summer. But let me give you a first non-trivial example when it's still a topological theory, sort of quasi-topological theory, but things actually work very nicely. So if you combine the structures and you know what you want, you can get stuff very easily. So in remaining time, what I will talk to you, there are many more examples, of course. It's just 2D Young-Mills. So as you know, 2D Young-Mills can be written, so Young-Mills, of course, this is something like trace of f wedge star f. And of course, we can write it in the following form. So we can write this as a first order formalism. So we can write fa dab eta ab plus 1 over 2 fa star f, phi b eta ab plus 1 over 2 phi a ab ac f a b c. So if this term is not there, this is what's typically called BF theory. If it's this term is there, and of course this is just a scalar, so we put a volume form here. So it's actually very easy to construct Chern-Simons form for this guy, and you can do in the following way. So let me write for you a complex. So I will have 1 form, 2 form. So this is D will be 0 form, one form, two form. So here there is arrow, you multiply by volume. So now this is where your field A sits. This is where field phi sits. This is where ghost will sit. And whatever remaining things, it's basically what people call antifields. So what you can do the following theories. So you can take a T1 of sigma 2 and put extra coordinate zeta. So this coordinate of degree 1. And this you just map to G of 1. So now let me write for you the action, and then you can actually check that. So if you don't know BV, don't worry, I will tell you maybe in a moment more elementary things. So basically what I'm trying to do, I'm trying to put everything in a Chern-Simons form. So if I look at this superfields, I can call it A, and this superfields, I can call it phi, and then I'm basically constructing another superfield. So it will be A x theta plus now zeta of phi of x theta. So now my theta is only 2. So I have only theta 1, theta 2. But to imitate Chern-Simons, I have to introduce another auxiliary coordinate. So then if you introduce your Dirac differential, your differential as follows. As a volume form d zeta. So of course you can check that because there is nothing here, there is nothing here, this is actually a differential. And what you can check is the following, that if I now write to you the superfields, so if I write to you this section exactly as before, A, D, B, eta AB plus whatever, let's put 1 over 2, 1 over 6, eta A, eta B, eta C, F, A, B, C. Now the only my measure is now 2 theta dxi, because this 3x. So I will, this action at physical fields is exactly this. So this is a Chern-Simons formulation of 2D Young-Mills in BF. Okay. So then what one can do, one can actually, let's say we want to have this color-kinematics. So we need to find, so the question is the following question. We need to find this D dagger with all these properties, with all properties. So you can actually do it. So let me not, tell you too much things. So it's a sort of mathematical problem how to do it. But you can do it, and actually with all properties, there are only two answers exist if you want to satisfy. So I will write to you a diagram. So this is differential. I have to write to you operator of opposite degree. So this looks as follows. It will be 2D dagger, and there is, of course, exists a complex conjugate answer. I star minus I. So important thing, it's not obvious, but if you take this operator, the anti-commute, you get a Laplacian and all other properties. And there exists either this operator or its complex conjugate, which satisfy everything. And actually, you can write this operator in superfields, and this is second order operator. So what's the upshot? Of course, now what you can do, you can put a gauge fixing here. So typically, the gauge fixing you are doing, again, in a way, you will never dream an old story to do like this, because if you stare at this section, I mean, you will put a Lorentz gauge typically here. But now what I'm telling you that this actually tells you that you have to look at strange now new things. So I construct this operator, so it's sort of generalized Lorentz if you wish. Now, for example, I have to look at, well, let's decide it. Let's look at the kernel of this operator. So if I look here, so this is my physical fields, right? So I have to look at the kernel of this operator. So the kernel of this operator will be 2d dagger A plus I phi equal to 0. So that's a gauge. Of course, it's a complex gauge. I have to complexify. I can go to Minkowski, and this will be some version of light cone gauge. But important thing that if I do my gauge, so I have to relate auxiliary field, this phi, to this Lorentz type of holomorphic gauge. Again, you will not dream to introducing this weird gauge, but it's a valid gauge. It satisfies everything. Now, the upshot is the following, that again, this is due to this all this formal nonsense that what is going on. So I start this section. So my gauge is telling you, let's concentrate only on the physical fields for the moment. So I just have to express phi. So if I want to do trees, for example, I just need to express phi in terms of d dagger. I plug it in there. So then actually, let me tell you what's action, and then I will finish. And so if you concentrate on physical fields, you get the following funny version of action. So you can introduce here the pairing between A01, A01. This will be, I mean, the pairing, you can think of this. Basically, you can put here I, just that's all. Right, and then the main thing that if I want to write for the trees, I will get the following. I will get A10A, A01B, eta AB, minus, then I will have this pairing. So I will introduce now a bracket. I will tell you in a moment. It's 10A, 10B, A01, C, FABC. So this bracket will be now generated by the dagger operator. It's again second order. It's actually generated bracket. This bracket is invariant. So you will have a bracket of basically holomorphic, holomorphic vector fields, and you will have anti-holomorphic bracket among each other will be 0. So you have to prove all algebraic property that it works. But again, he will be basically a full color kinematics duality, and you can extend to loops, etc. So again, you can play this game, and I mean, the funny thing is that what's interesting about this game that you start, so you can build whole machinery. And again, I'm not telling you because it's much more complicated about 4D Young Mills. Hopefully next summer or whatever, I will tell you more. But basically this pattern will repeat itself. The only thing is that gauge fixing should be much more exotic, and sometimes it's not a second order. But a lot of properties restrict you for very, very particular gauge fixing, which would have very, very nice algebraic structures. And so this is basically an example. And actually a lot of the things formally, it will go to the curved manifolds. You can say it's not that it's not clear how much it's useful in direct calculations, but you know, surprisingly all these algebraic structures are sitting there. We just did not pay attention to those guys. Yeah, I don't know what else to say. I mean, there are much more stuff. I have many more examples. And again, in a way, at some point, it goes very, very formal and sort of sorry for being a bit orthogonal to the workshop. I mean, but since I'm doing this BV type of stuff and amplitudes, I decided to talk about this. Okay, thank you for your attention.
So questions?
Yeah, for D, we always say what's the formalism.
Yeah, exactly.
But here, like, so BF plus B squared.
So what you are doing there, this is basically what Castello is doing. So you will take, you know, so you, as you said correctly, will write phi dA plus phi AA, right? So this will be BF. But then what Castello is suggesting, you put a self-dual guys, and then you write phi plus square. So up to topological term, this is Young-Mills. And then you can extend everything. So this is already in Castello book that this theory you can extend and write as a formal Chern-Simons theory. The only problem is that there is no superfields in normal sense. I mean, there is still differential graded algebra, but it's not freely generated like typically you have with thetas. Yep.
Is there a double copy of this Chern-Simons?
Formally, you can write this stuff. There is expectation, but the main thing that, I mean, this is where I think it becomes not very scientific. I mean, you know which amplitudes to calculate, but you have to find the correct gravity theory, etc. I mean, we have some guesses, but it's not clear. I mean, for 2D, I don't know. I mean, maybe it's whatever, Jack, if this JT gravity, I don't know, but no one calculates amplitude there. Again, you have to do something illegal. I don't know. But the main thing that you have to match this sort of gauge fixing here with gauge fixing here and write it down. So formally, I know how to write a double copy, but I don't know from which theory it's actually coming up. Yep.
So if I understand correctly, the general strategy for many of these theories you're saying is to write them down in some kind of Chern-Simons form, find the differential, so that you have a generalized Lorentz gauge.
Right.
You can exhibit color kinematics.
Right.
So two questions are, well, to what extent do you expect this to work out in generality? So you have 2D, 3D, and 4D now, but beyond that. And also the algebra of the kinematics, the kinematics algebra, is it going to be the same that you showed us with this?
No, it will change. It will, I mean, depend from theory very, very much. So I already gave you Chern-Simons example. And there the algebra is basically already generates from differential form with d-Dagger operator. And then, for example, I gave you 2D Young-Mills theory. And this will be a differential forms with d-Dagger operator. It's already two different algebras. And then you have to keep going on. For example, for 4D Young-Mills, and I touched only topological or quasi-topological terms. So I did not discuss on shell. What is going for 4D, you basically get operator of higher order. And it's not satisfy, I mean, Jacobi, but it will satisfy Jacobian cohomology. So it means that, I mean, guys on shell, I mean, the states outside should go on shell, etc. So it's a bit more tricky. So you will get this structures which, you know, people get, I don't know if you know, like current brackets and generalized geometry and stuff like this. So they get this Lie algebras which fail to do it. But the main problem here is, this is my complaint about other literature. I mean, you should not say everything L infinity or whatever. I mean, you should study theory by theory and you get a very, very different algebras and, you know, things are hiding in details.
Is there something special about pure gauge theory, or do you think this procedure of yours of turning it into Chern-Simons theory can also be done when you have matter?
No, I think you can do it with the matter. I mean, the main thing that things are getting complicated, you know, I mean, even for Young-Mills, I think Castello wrote his book, whatever, 8 years ago. I mean, this is not a common knowledge that for the Young-Mills is a Chern-Simons theory, very exotic. I mean, right, but I think, you know, my philosophical statement that everything is Chern-Simons in this world. If it's not Chern-Simons, this is a bad theory. I mean, but the thing is that this statement to show, to prove, you have to work a lot. You take a concrete theory, you do it. But eventually, you see there is a statement which was proven by Kontsevich. So if you have graphs, very complicated graphs, and you have to start to write using this graph cohomology. So it's basically contracting the H and putting some appropriate sign. This is what you use in word identities. So what Kontsevich proved that if you take graphs, whatever vertices there are, cohomology sits only on trivalent graphs. So it's basically saying that, I mean, all other higher vertices should be resolved and they're not important physically. But again, at the level of general statement, this is bullshit. I mean, to make it precisely work, this requires a lot of hard work, etc. So, my message is that you have to do theory by theory, and it's very easy to make a general philosophical statement, but if you go to details, it becomes very, very nasty.
What about 3D?
Hard and harder than 4D. For example, I mean, it's I know how to write 4D Young-Mills Sachin-Simons. I don't know how to write 3D Young-Mills Sachin-Simons. You would believe that 3D Young-Mills should be simpler, but in 4D, what saves the world, it's the self-duality. So this self-duality effectively allows you to introduce the metric. And basically, the Young-Mills depends only on conformal structure. 3D, I don't know. So I would believe, but I tried, I failed. So.
Do people know about double copy for 3D transformers without this trick? Did they work?
Well, I mean, people wrote some papers. I think Hendrik and Maurer point out something. Then it was, yeah, there is also this double copy. For example, the Holm, this collaborators wrote thing that you can also make a not double copy theory in twice more dimensions. So basically, they said that Kodaira-Spencer will be, so, it's a big industry. The question is that if you want to stay in the same dimension, so you can write formally double copy, but you would like to identify with a concrete physical theory which gives you exactly the same diagrams, but in particular gauge. That's, of course, very, very hard. But for example, for some 4D Young-Mills and supergravities, there are very exact identifications have been done.
Is there some geometric description of this pairing in higher dimensions? And maybe also of this Chern-Simons draw, because we kind of have a lifting pairing, we have a intersection pairing, and some dimensions.
Well, so it depends. So this pairing, if I look at different theories and I introduce this generalized D-dagger operator, then this can be tricky. Now, if I just stick to a standard D-dagger operator, then, for example, that's example I did not tell you. So, for example, I could write for you 4D BF theory and use D-dagger, and they will be corresponding pairing there, and they will be corresponding bracket there. So I don't know what's the geometrical interpretation of this pairing, but what's important that this pairing still will satisfy algebraic properties. So I could have, in 4D, I can introduce for you the same pairing between forms. But now what's important thing that now one form should be paired to two form, for example. So I will write to you A tilde as A wedge xi, where A tilde equal to D dagger xi. Now you can see I cannot pair one form with one form in 4D, right? But I will pair for you one form with two form. And that's exactly what you need in BF theory, because when I will write to you this term, I am basically telling you that if I look at the image of the dagger, this term will be the same as A Laplace phi. Right. But of course, what's important thing that once you move to dimension, the gradient is changing, right? So with this pairing in 3D, I pair one form with one form, but if I go to 4D, I pair one form with two form. If I go high up, etc. So in a way, it takes care of this in a smart way. But of course, this pairing is relevant for this topological BF type of theories when you have D-dagger. In other theories, you have to invent something more exotic. No. Well, so let me make the following philosophical statement. With enough fields, you can always, you have to always introduce enough fields to make it cubic. Cubic is the only answer to the life. All other guys is just basically misleading interpretation. So, for example, even if you go to 5D Chern-Simons, what I'm telling you, if you want to study this Chern-Simons, you have to introduce more fields and write these guys with the cubic interactions. Absolutely, as a normal Chern-Simons. Again, I didn't sit down how to write it, but roughly I know how to do it. It's can be done.
You say that it's possible to do by introducing extra fields?
Yeah. Do you want to bet on a bottle of wine, and I will write an article and then. I mean, there is a statement that Chern-Simons it's a correct theory all the time, and so you can. I mean, the 5D Chern-Simons, when you write these high things, it's very hard even to analyze degrees of freedom. You have to introduce more fields, etc.